And the final talk of this session will be from Ryan Currier, and he'll be talking about frozen precipitation in the Olympic Mountains during Olympics.
All right, hi everybody. Yeah, I'm Ryan Currier. I'm a graduate student at the University of Washington, working with Jessica Lundquist, and I was in charge of setting up the snow camera network that Bob was talking about earlier. And we used those snow depth observations to evaluate WRF and PRISM in water year 2016. So this is similar to a figure you've seen before. This is the snow measuring system in the bottom right, which just consisted of marked PVC poles and a time-lapse camera placed in the trees. So relatively simple compared to radars and other rain gauge observations. And you can see that they're located farther in the mountains than the other observations. To give you an idea of what these time-lapse camera images actually look like, you can see entire water year here, and you can see that our poles became buried and our poles became bent, and once they become bent, they also come back, and some poles were buried before the season even started. So it sounds simple, but it actually had a lot of challenges. Fortunately, we also had Airborne Snow Observatory observations, which is airborne LiDAR, and these could fill in the voids for when we had the poles, or when they became buried or too bent. So we had two sets of these observations, and we could actually build 60-meter bounding boxes around the location of our poles, which are shown here. And then we could remove the trees, because sometimes LiDAR has trouble seeing through trees, and we're only focused on open areas because we're looking at accumulation. And as I mentioned, I'll be using those observations to evaluate WRF, which is a dynamical model I'm sure most of you guys are familiar with. We got these data from the Northwest Modeling Consortium at the University of Washington, which is run by Cliff Mass. And we are only looking at the Thomson microphysical scheme. As we talked about earlier, there's a lot of other microphysical schemes. And we're using the output of a total precipitation, snow, graupel, and hail at a 1.33 kilometer spatial resolution. In contrast to that, we have a statistical model, which is PRISM, and that's just an annual climatology map, and it's widely used in hydrology, and it's derived using gauge observations, and then using weights based on topography and coastal proximity. You can get a complete spatial estimate on an annual basis of precipitation. And you can take the gauge observations, which are shown here in black, and for instance, at the remote automated weather station down here at the lower Quinault, it's estimated to be 2 meters of precipitation per year, but at our sites, these snow depth observation sites in the yellow crosshairs, it's estimated to be about 4 meters of precipitation per year. So you would take your gauge observations and multiply it by 2 to create a spatio-temporal data set. So we can ask some research questions. Is PRISM or WRF better able to simulate frozen precipitation over the course of an entire water year? And then we can look more specifically at a smaller time period. So we focus on the OLYMPEX intensive observational period, which is earlier in the snow season, and that's when we had a bunch of airplane observations as well as a lot of radar observations. And then we can ask whether these errors are spatially dependent. Is WRF overestimating precipitation in one region of the Olympics or underestimating in another? To answer that question, we really need a hydrologic model because we have estimates of total precipitation, and we need a model that can partition the precipitation. And as you saw, our observations are of snow depth, and so we need a model that can accurately simulate snow depth. So we chose SUMA, which stands for the Structure for Unifying Multiple Modeling Alternatives. All hydrologic models basically use this scheme to partition precipitation, which depends on a critical temperature threshold, which is shown by this black bar. And so at some temperature, all your precipitation becomes snow, or it's rain. And in between, within some range, you actually have a mixture of precipitation. So we evaluated our decision at the 4 snowtell sites in the region to get what was simulating So the model is simulating snow water equivalent accurately. And this is kind of remarkable to me because 40% of the winter precipitation at the SNOTEL sites falls between -1 and 2 degrees C. So this choice and your critical temperature threshold is actually really important. And a 0.2 degrees C change in that center or median value results in a SWE change of 2 to 8%. So here I'm showing a 1.5 degree change in model SWE in the gray shading. So we evaluated it, the model at the SNOTEL sites so it was accurately simulating snow depth. And here I'm showing in the green box and whisker plots the distribution of values from a 60-meter bounding box from the LiDAR observations. And in the black dots, we have our observations from the time-lapse camera network, which have some gray shading associated with uncertainty. But you can see that the median value on the February flight date agrees well with our observations from the snow depth pole network. And then I'm plotting here PRISM estimates at this one particular site and showing that it generally agrees well with our observations on a total annual water year timescale. And just noting that PRISM is using the linear partitioning scheme. Here we can add in WRF, which actually you can have two different ways of partitioning your precipitation. One is using a linear precipitation partitioning, same as PRISM, and the other is using the microphysical output to actually calculate the fraction of precipitation that is rain in an individual event, and then running the model forward with total precipitation estimates and using the rain fraction to partition precipitation. And you can see that you get a drastically different answer for the same precipitation. If we wanted to look at all of our sites instead of just the one I used as an example, these are differences compared to the March 28th observations, which is near peak snow depth. And you can see that PRISM and WRF, when WRF used the microphysical partitioning scheme, were generally unbiased. The mean absolute errors, which are shown in the horizontal lines, were around 20%. And they were unbiased, but WRF LP, which used the linear partitioning, was generally biased low. If we wanted to look at just the intensive observational period, so where the shading is, we can break it down into the entire period, so where all the shading is from November to mid-December. You can see all WRF, PRISM, and both simulations WRF had similar absolute errors, but WRF LP continued to underestimate snowfall, as it did over the entire winter. And then the largest snowstorm, which is really just the 4th through December 23rd, WRF, with the microphysical partitioning scheme to partition precipitation, was unbiased and had the lowest absolute error. While PRISM generally was biased low during this time period, and PRISM over the course of the winter we found, or even over the course of the entire intensive observational period, had errors balanced out, and we attribute that to it being an annual climatology map, so it doesn't know anything about the synoptics of individual events. While WRF is a dynamical model and can simulate the synoptics. Lastly, just looking at the spatial distribution of errors. So we're zoomed in on this one region of the OLYMPEX, and these are PRISM errors. So a downward facing triangle means it underestimated compared to observations. And if it's colored, it's outside of the range of our model uncertainty. So we're fairly confident that our precipitation during snowfall events is being underestimated at these regions. And by that itself, we can't conclusively say there's really any spatial patterns, but I do want to draw your attention to this one region of the Olympic Mountains where all of these estimates are too low. So here's a true color image to show you that we're really at the crest of the Olympic Mountains. And if you look at the PRISM map for that same region, you can see the region of maximum precipitation estimated by PRISM is farther west than the crest, and that the crest has lower precipitation estimates, and that might not actually be true, and PRISM might be biased low at that region. If we look at WRF with the microphysical partitioning scheme, which seemed to be doing better than using the linear partitioning scheme, we find really no spatial patterns, and any errors are probably due to some local effects in the model. So with that, just summarizing, PRISM and WRF, WRF with the microphysical partitioning scheme were both unbiased and had absolute errors around 20%. WRF with the microphysical partitioning scheme had the lowest error during the largest snowstorm. PRISM had errors balanced out. PRISM may be biased too low near the Olympic crest. And hydrologic modelers should consider using WRF to partition precipitation and use the estimates of precipitation from WRF going forward, especially in regions where you don't have calibration data or PRISM maps. So thank you.